In this video we will see how to derive the proof of a Minkowski inequality in L2, where we have U1 plus U2 in L2 norm, where omega is a bounded region in n-dimensional Euclidean space. This is less than or equal to the norm of U1 function in L2 of omega plus the norm of the function U2 in L2 of omega. It reminds a little bit of the triangle type inequality, like this one here. How do we prove this result? We start with U1 plus U2 L2 omega squared, and thus but by the definition of the L2 norm is going to be the integral over omega U1 plus U2 squared. U1 and U2 are real valued functions, and this is a measure on the omega, the measure on omega, on the domain omega. So it's the integral over omega U1 plus U2 squared d omega. So that one is U1 squared plus 2 U1 U2 plus U2 squared d omega. So that's going to be the integral over omega U1 squared d omega plus 2 times the integral over omega U1 U2 d omega plus the integral over omega U2 squared d omega. That's going to be the integral over omega U1 squared d omega plus 2 times the integral over omega U1 U2 d omega plus integral over omega U2 squared d omega. But that one is going to be less than equal to the integral over omega Okay, let's add one more page. U1 squared d omega plus 2 times when we have a quantity that is less, that's going to be less than the absolute value, the integral over omega U1 U2 d omega, because when we have a is going to be less than or equal to the absolute value of a, plus the integral over omega U2 squared d omega. And then we have triangle type inequality for the integral over omega U1 U2 in absolute value d omega plus the integral over omega U2 squared d omega. Okay, now for the second term we're going to use the Cauchy-Schwarz inequality. It's going to be the integral over omega U1 squared d omega plus 2 times the integral over omega U1 squared d omega to the power of a half times the integral over omega U2 squared d omega to the power of a half plus the integral over omega U2 squared d omega. And the first term is the norm of U1 in L2 squared plus 2 times the norm of U1 times the norm of U2 in L2. L2 I omitted the omega, is implied that is on the bounded region omega, plus the norm U2 in L2 squared. And that is just U1 L2 plus U the norm of u2 in L2 raised to the power of 2. So far we have that the norm of u1 plus u2 L2 squared is less than or equal to the norm of u1 in L2 plus the norm of u2 in L2 squared. We raise both sides to the power of a half. And that's gonna give me the norm of u1 plus u2 in L2 less than or equal to the norm of u1 in L2 plus the norm of u2 in L2. And that concludes the proof.